great. Thanks.
Ready for the next print?
Yeah, for the next one, yeah. Hi, my name is Jurij Licen, and I would like to talk to you about architectural design adapted to 3D concrete printing technology. The relationship between technology and design has always played an important role in how architects conceive buildings. Invention of new tools brings about significant changes in building design. This can be seen in the invention of curve drawing tools and the complex geometries of Bernini and Borromini in the Renaissance. Later on, the invention of materials such as steel and technologies such as the elevator brought about an expansion of skyscraper buildings. Around the same time, Le Corbusier was able to make use of a new material, reinforced concrete, to conceive a completely new typology of buildings based around slabs and columns. Today, with rapid expansion of digital technologies and tools for fabrication, we are able to 3D print concrete buildings. This is an example of a house being 3D printed in Belgium. There are lots of researchers experimenting with tools to design smaller pavilions and houses. However, most of them end up looking very similar to the houses we know today, with extruded vertical walls and slabs that are cast into traditional formwork. The aim of this research is to try to design new buildings that better respond to the opportunities and limitations of this new technology. One of the main benefits of the technology is optimization of material use. This is an example of a girder where material is placed only where it is absolutely needed. With the use of computational tools and structural analysis, an optimized cross-section is designed, which is later fabricated in pieces and post-tensioned with cables. One of the more important limitations of the technology is the angle at which we can print. The more straightforward approach is to slightly cantilever the stacking layers in order to achieve an overhang. With this approach, we can build at angles around 40 degrees from the vertical. Using variable material distribution, the inclination could be increased to around 60 degrees for certain more tubular cross-sections. Freshly deposited concrete is structurally weaker because of its semi-liquid state. It is therefore in danger of collapsing under its own weight. Certain prototypes perform better than others because of their geometry, which is able to support the material. Lean vertical walls, for example, represent problematical areas. Digital simulations of the print help us better understand the relationship between material rheology, geometry, and form that is suitable for printing. With these properties in mind, the research focused on exploring the relationship between design and fabrication on a small-scale prototype of a usable object. A chair was chosen because it was feasible to fabricate in 1:1 scale, while at the same time maintaining some of the functional and design constraints that you would also face when designing a building. The design process begins with a 3D sketch of the chair done via polygon modeling. The use of sub-D tools makes it easy to manipulate complex double-curve geometry. During the process, the model is constantly evaluated for printing angles and structural stability. Using this technique, a catalog of different chairs was modeled. To better understand the relationship between geometry and structural stability, some of the prototypes were 3D printed in plastic. By adding complexity while maintaining continuous curvature, models became more rigid, as shown in the top two examples. Further tests done with digital structural analysis using Caramba 3D confirmed the assumption that adding complexity while maintaining topological continuity increases structural stability. Simulations of the printing process show some of the potential failures that would occur during print. The top two examples have large flat areas where material begins to buckle under its own weight. Printing was done in collaboration with Incremental 3D and was executed in 1 day. The setup uses an ABB robotic arm with a custom-built concrete extruder. The digital model is transformed into a series of points for the robot to follow and deposit material. Two prototypes were produced. The first one took about 28 minutes to print and weighs around 150 kilograms, while the second one took 21 minutes to print and weighs 122 kilograms. The question is, where to go from here? What is next? One of the things this research will have to answer is how to upscale prototyping. How do we use it for housing or some other typology? Do we use reinforcement? And how do we evaluate the new aesthetics? The most important question to answer, however, is what is the next domino house?